Okay, ladies and gentlemen, let's continue with chapter 4 on transient heat conduction. There are 4 major parts in this textbook. The first part is the lump system approach. The second part is long plane walls, long cylinders and spheres. The third part was the semi-infinite solid. Semi-infinite solid is a solid where the temperature doesn't change, although things might change very close to the surface. Okay? And then the fourth part, which is the multidimensional systems. And with the multidimensional systems, we've seen that we can make use of the principle of superposition or the principle of the product rule to use all our previous work that we've done to solve 2-dimensional and 3-dimensional heat transfer problems through other types of bodies. And these bodies, or some of them in any case, have been summarized in table 4.5. So where previously we had, let me just enlarge this, and Aaron, if you can also just zoom in on it. Okay. So previously, if we had the infinite cylinder, very, very long, what we can now do is we can look at what happens to that surface also, to close to that surface, which means that the heat transfer is not only in the R direction, it is now also in the X direction. And that is just the solution of that would be the product of those two solutions. And then the same with the short cylinder. With the short cylinder, it is the product of the solution of a cylinder and that of a wall. And that was the problem that we've started doing. So that is example 4.8. It is short brass cylinder. And that short brass cylinder, these are the dimensions. The temperature on the outside, 24. The heat transfer coefficient, 60. The initial temperature is 120 degrees Celsius. Other properties are given. And they ask us to determine the temperature exactly in the center of the short brass cylinder, temperature there and also the temperature there. It's not exactly the same as in the textbook. In the textbook, I think they only calculate that temperature and they also use Heisler charts. So I have a little bit of a different approach. I'm not using the Heisler charts. I'm going to do it theoretically, and there are also some more points in there because I'm trying to make a very, very important point in terms of how you should use this to get the temperatures in very complicated geometries. And if you follow the philosophy in terms of what I'm trying to show you, then it will be very easy. Otherwise, it can be extremely confusing. You lost yourself very, very quickly and you don't know where you are. Okay. So, what we did with the previous lecture, unfortunately we couldn't finish. We said that according to this table, the solution of this short cylinder is the solution of a plane wall and a cylinder. We just need to multiply them. Okay. But we first need to get the solution for the plane wall and the cylinder. And specifically, if we are interested in the temperature there, then that would be where R is equal to 0 and where X is equal to 0. So previously, when we had the plane wall, we had X being measured from there. So it is very important that in the placement of our coordinate system, we look very carefully at the dimensions. That can be, many people make a mistake in not choosing the correct dimensions. Okay, so in terms of the plane wall, we need to get the temperature at the center. Now previously, when we looked at the plane wall and we said we want the temperature at the center, we were sort of thinking of the temperature there. But remember, it is a one-dimensional problem. This thing is very, very long, and boundary conditions are on that side and on that side. So this is actually the temperature on a line everywhere. Okay, it's not the temperature only at one point. Okay, so how did we do it? We calculated firstly the Fourier number, or the non-dimensionalized time, which is 8.4, the Biot number. The Biot number tells us the delta T's are small. Okay. The Biot number, because it is small, means that the temperature difference inside the body will be small. We've looked at the equation, we've reduced it, the roots. We said we're only going to look at the first term because tau is larger than 0.2. So it should be, if we only use the first term, then the solution should be within 2%, which is good, which is fine. Okay. So in that case, we only need to use the first term, or n equal 1, so the constant 1 and lambda 1. You can solve it in ease or wherever you want to. You can solve those roots. You can get it from the textbook. Those are the two answers. So with that, the non-dimensionalized temperature is equal to that. With the previous lecture, I forgot to put in this value. Okay, so I hope you've all picked it up, because I think by now you know that there's a difference sometimes between what I mean, what I say, and what I write. It can be three different things. Okay, so I forgot to add that, but as you can see, it is in any case almost 1. And then you can solve the temperature on that line, which would be 97.21, or the non-dimensionalized temperature, which would be 0.76. So the same for the cylinder. That is the line, and what we are doing now is we are getting the temperature everywhere on that line. So here we've used C, and here we've used S. Okay. So again, we calculate the non-dimensionalized time. It is 12.2, the Biot number. Biot number is small. The gradients inside with temperatures should be small. We go through the process with the equations. We only need to look at n equal 1. There's the equation. Get lambda and A. Calculate the non-dimensionalized temperature from where we can calculate the temperature and the non-dimensionalized temperature. Again, yesterday I forgot to put in that value with that one also, and that is where we've stopped. Okay. Any questions up to now before we continue with the rest? Are you all with me? Okay. Let me just see if I can figure out where to continue. Right. Okay, so what we now need to do is we obviously need to get the temperature there. Okay. So the temperature T0 is obviously where x is 0 and r is 0. Okay. Now where x is equal to 0 was the C line. When r is equal to 0, very easy, is the S line. So where the two intersect, that would be the temperature. Okay. So from table 4.5, we've already seen it. The non-dimensionalized temperature, XRT, is equal to the non-dimensionalized temperature for the plane wall, which is a function of xt, multiplied by the non-dimensionalized temperature for the cylinder, which is a function of R and T. With the previous lecture, in table 4.5, that is the solution for a short cylinder. And that is what we are interested in. So if we look at all the X's and the R's, let's just put it in, because again, we take very, very simple and easy baby steps before we start making things more complicated. So X would be 0, okay, R would be 0, okay, the time is 900 seconds. I'm just going to put in time there for a moment. It's multiplied by the non-dimensionalized temperature for the plane wall at x equals 0, multiplied by the non-dimensionalized temperature for the cylinder, where R is equal to 0. Okay. So here we can see the types of solutions that we need. Okay. X equals 0 and R equals 0. Therefore, we can say, and depending the type of nomenclature that you want to use, I'm going to use CS. Okay, and CS means the intersection of the line C with the line S, okay, the intersection, or theta 0, okay, and that would then be equal to 0.76 multiplied by 0.5163. Okay, here we can see 0.76 and 0.5163. Okay, so that one was for C and that one was for S. So theta CS is the intersection of the C line and the S line, which is then equal to 0.392. Or the non-dimensionalized temperature, if we write it in that format, okay, which is then equal to the temperature we want to solve minus the temperature on the outside 25, the initial temperature 120 before we started the cooling, minus 25 is equal to 0.392. This non-dimensionalized temperature that we've solved now. Theta, okay, it's just a non-dimensionalized temperature. And it's in the table. Okay. So from it we can solve the temperature at the center as 62.3 degrees Celsius. So if we, just to make things clear, if that is the plane wall, okay, that is the cylinder there, like that. My sketch isn't that good. Let me try again. Okay, let me rather do it like that. I think it's easier. Okay. So we had that line there, which is the C line, and we have the S line, and the intersection of the two is this temperature T0 that we were looking for. Okay, very, very simple. Okay, right. Okay, now let's look at how are we going to get the temperature at that point there. Okay. Now before I start with the calculations, what would you suggest? If you look at these two solutions of how to get the temperature exactly in the center. Okay. If we want to move to that point there, okay, remember our coordinate system is also given in the sketch. So that is R and that is X. And we've been using that all the time. Okay. Okay, so if we want to move to that point there, that is where X is equal to 60 millimeters. So that is that line there. Do you agree? But we're still on the center. So to get the temperature there, we need to take this problem, but we need to solve the temperature on that line there. And again, multiply it by the center temperature, and that will give us the temperature at that point there. Okay, so let's do that. Okay, so the temperature at the top, and in terms of the sketch that we've made previously of the plane wall, that is 2L, which is 120 millimeters. But now we need it on that line there. Okay, and let's call that line E. Call that line E. We have to go through the same calculations again, okay? So I'm not going to write out everything in detail. I'm just going to write out the most important ones. You can go home and you can go home and you can check if it's all okay. Okay. So the non-dimensionalized temperature is 8.48. If we look at it previously, it is alpha t divided by L squared. So it's still the same value. It's not going to change. L is there, and the Biot number also, everything is the same. So the Biot number is equal to 0.03273. Okay. In terms of the calculation now, where previously we've calculated at the center, let's look at the equation again, fundamental equation. The non-dimensionalized temperature is the sum of a few terms. Okay, ANE to the minus lambda n squared tau, but multiplied by cos lambda multiplied by x divided by L. Something like that. Okay. And n, we've said we only need to look at the first term again because tau is larger than 0.2. So the first term approach would be accurate enough, within 2%. Okay. Let's look at that term there. Okay. So we now have cos of lambda 1 multiplied by x. And x will be 60 millimeters divided by L, which is also 60 millimeters. Okay. They cancel, and the result is that we will have an additional term, cos lambda 1, which previously wasn't there. Okay. Because previously it was at x equals 0. Okay. And therefore, cos of 0 is 1. Now we have cos multiplied by lambda 1. Okay. So in terms of our solution, in terms of the non-dimensionalized temperature, if we want it at E, okay, because that is our line, then it would now be equal to A1E to the minus lambda 1 squared multiplied by tau multiplied by cos lambda 1. Right, now if you've done many of these calculations, then you'll immediately know that the only difference between this solution and the one of previously, okay, is the cost term. So you just multiply by the cost term. Okay, okay, that one there. And if you go through the calculations, then you will see it is equal to 0.7478. Okay. And that is the non-dimensionalized temperature, is TE minus T infinite divided by Ti minus T infinite is equal to 0.748. And all the temperatures are known except TE. So TE can be solved as 96.04 degrees Celsius. Okay. Now remember, that is not really the temperature there at the moment. That would just be on the plane wall on that line. Okay. We still need to get the temperature now at the intersection of the two. Okay. So the temperature is where X is equal to 60 millimeters and where R is equal to 0. So again, if we now look at the solution of the short cylinder, okay, which is theta XRT, let's just write it down quickly, is equal to the solution of the plane wall multiplied by xt multiplied by the solution of the cylinder, RT. So theta We want it now where x is 60 millimeters. Okay? So we've got the 60 millimeters here. R is still 0. And t is 900 seconds, 15 minutes. I'm just not adding it. It's equal to the solution for the plane wall where x is 60 millimeters. The time is 900 seconds and multiplied by the non-dimensionalized temperature 0T. Okay, let me just repeat. Okay, the non-dimensionalized temperature in general, XRT, is the solution of the plane wall. The plane wall would be a function of x and t, and the cylinder would be a function of r and t. Okay, in this case, x is 60 millimeters. If we compare it to previously, it was at 0. Okay, now it is at 60 millimeters. R is still at 0. T is 900. Plane wall, x 60 millimeters, and RT where R is equal to 0. Okay, so the result of that is that now we are going to get the solution of the lines E and S, where they intersect, the lines E and S. Okay. Which would be the temperature, the non-dimensionalized temperature, as we previously defined it at point T. Okay, and that would be equal to 0.7478 multiplied by 0.5163. Okay, let's just see if we can get all these lines. Okay, this value of 0.748 is for E, the E line. Do you see it? And the other one was the S line. The S line, 0.5163. There it is. Okay. The S line. You all with me? Okay. So the result of that is now that we can obviously go and calculate the non-dimensionalized temperature. T infinite, Ti minus T infinite, and if we multiply those two terms, then the result is something like 0.386089. Okay. And from this, we can now solve the temperature at T, which is 61.7 degrees Celsius. Let me just show you the lines again, just to make it clear. Okay. This line is the S line. Okay. This line was the C line. Okay. And that line there was the E line. Okay. This temperature here is the temperature at the top, 61.7, okay, and that temperature there we've previously solved is 62.3 degrees Celsius. Any observations? What can you guys say from this solution? In terms of the temperatures, if you look at the temperatures, what conclusion can you make from it?
Basically the same.
Mm-hmm. Now, basically it's the same as expected. Why? Because the Biot numbers were very, very small, and that is why we've written here the delta T's are very, very small, and the result would be that the temperatures would be very, very close to each other. So, many bright sparks in the test and exam is then going to say, forget about all this rubbish. I'm just going to use the lump system approach. It's going to give me a good answer. Do you think that's a good defense? Mm-hmm. What would you expect? What would you expect of this temperature here is going to happen with that temperature there? If we look at this, the Biot numbers are small. 62.3, 61.7 is it's actually both temperatures is 62 degrees Celsius. Okay. What would you expect of that temperature? Would you expect it to also be very close to that? Who do not agree? So everyone say that is the case. You say that is not true. Okay.
The plate is at a higher temperature.
The plate at a higher temperature, do you mean the solution there?
At E it's 96.04. But isn't that sort of like an average, or what are you guessing?
I don't know, let's see. Okay. Let's see what happens. So, now we want to get the temperature TR. Okay, there's a question before we continue. Ladies and gentlemen, please, I cannot hear.
The temperatures at 0 and at the top there.
Yeah.
60 something.
Sorry, what about them?
What about those temperatures that you calculated in the formulation?
The temperatures that what?
That you calculated the TC for 97.21.
Yeah.
But 97.21.
Yeah.
What does that temperature represent?
Okay. Okay, the question, okay, as anything can pick up, okay. So the question is, I mean, we see other temperatures here which are very high, 97.2, and we see the other one of 74, okay. Remember, that is for a plane wall only, okay. So that represents the case if we had a very, very long plane wall, the temperature on the outside 25, the temperature on the inside 120, so that's not a short cylinder, that is a long plane wall, okay? And that for a long plane wall would represent the temperature on that line, okay? But now the cylinder, we have a short cylinder, and the result of that is that the solution is the product of the two of them, okay? The long plane wall and the cylinder cutting through each other. So this is not a physical thing. This is not relevant to this. This is just one of the steps that you need before you use the product solution. Okay. Okay. So this would only be correct if that was the case, was a plain wall and not a cylinder like that. Okay. Right. So let's look at the temperature TR. Now, in getting the temperature TR, if we now look at this problem here, we need to move to this point there, okay? So to get to that point there, we can get there if we use R equals 60 millimeters. You see? If we take this solution for R equals 60, then we are on this line. If we take the plane wall for L equals 60 millimeters, then we have that line. And that intersection is then going to give us the temperature at TR. Okay. So, at TR, again, we have the plane wall case and we've got the cylinder. Okay. Now, the plane wall case would be for X 60 millimeters. Okay. And for X, so for X equals 60 millimeters would be this solution here. Okay. So if we look at that, then it would be that line there. Okay. And that would be a non-dimensionalized temperature of 0.7478. Okay. Now for the cylinder, previously we've looked at the cylinder where we've looked at the solution let's just go back to the cylinder again. The solution was on this line there. Okay, so now we need to get to that line there. Okay. So that would be the solution for the line there, and let's call it the P line. Okay. So now we need to get it for a radius of 50 millimeters. And just like before, this term is going to pop up, okay, with, in this case, some J values, the Bessel function values. They're in the table, or you can solve them. Okay. And it's going to look like that. The non-dimensionalized temperature is going to be equal to A1 e to the minus lambda 1 square multiplied by tau multiplied by J0 lambda n r divided by r0. Okay. And now r is going to be 50 millimeters. That one is also going to be 50 millimeters. So again, that one is going to cancel, and we've got this additional term which we previously didn't have. That is going to influence our non-dimensionalized temperature. Okay. Now the result of that is that the non-dimensionalized temperature on the P line is equal to 0.5093. You still with me? Okay. So, to get now the solution at R, which would be the intersection of the P line and the E line. All right, let's do it the other way around. The E line and the P line, okay, would then be the non-dimensionalized temperature of E and the non-dimensionalized temperature of P. Okay, the non-dimensionalized temperature of E is equal to 0.7478. The non-dimensionalized temperature of P is equal to 0.5093. Okay. That is the non-dimensionalized temperature, or the temperature at R minus T infinite, which is 25, the initial temperature 120, the other temperature 25, and the result is that the temperature at R is equal to 43.7 degrees Celsius. Okay. Okay, so we can see why the lump system approach is not going to work if we specifically are interested in the temperature maybe at that specific corner at the right. Okay. Any questions, ladies and gentlemen? Right. Everyone, take out a piece of paper, class test. Class test, and the test is the following problem. It is problem 492 in your textbook. If you do not have your textbook here, don't worry. I'm going to show you the information here on the table. Okay, while you get your paper, I'm going to clean the board, and then I'm going to give the problem to you. Okay. Running an error. Okay. Okay, the problem is 492. It says a 6 centimeter high or 60 millimeter high rectangular ice block, thermal conductivity 2.22, and alpha 0.124 multiplied by the 10 to the 7 is initially at minus 18 degrees Celsius and is placed on a table on its square base of 4 centimeters by 4 centimeters in size in a room at 18 degrees Celsius. Okay. So the ice block is at minus 18 and the room is at plus 18. Okay. The heat transfer coefficient on the exposed surfaces of the ice block is 12 watts per square meter degree Celsius. And disregarding any heat transfer from the base to the table, determine how long it will be before the ice block starts melting and where on the block will the first liquid droplets appear. Okay. So that is the problem. And obviously it has to do with multi-dimensional problems. Table 4.5, and there they are. Okay. Okay. Let me just enlarge it for you. There you go. So I think that's the one most probably that you're interested in. Then there's the solution. Okay. So the temperature at any position x, y, and z is the non-dimensionalized temperature of a plane wall, position x, the non-dimensionalized position of a plane wall in the y direction, multiplied by the non-dimensionalized temperature of a plane wall in the z direction. Okay. Question?
Can you write the question down?
So write the question down. I don't think we're going to have enough time for that. That is the ice block. Okay, so the ice block, all the properties given. It is at 18 degrees Celsius. That is 60 millimeters, 40 by 40. The heat transfer coefficient 12. At T equals 0, the temperature of the ice block is minus 18. The K value and the alpha, and you can neglect heat transfer from the base. The question, determine how long T it will be before the ice block starts to melt anywhere in the center or the corner or wherever you think it is going to melt. It's going to melt when the temperature is equal to 0 degrees Celsius. So that is what you need to get. You need to get 0 degrees and you need to get the time. Okay. 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 Are your names on it? Are you finished? Why not? Okay, stop. Okay. You have to give it in. So just give it in to my release after the lecture. But I want you to look now at something. And that is, there is the thing that we need to solve. So the coordinate system x, y, and z. Okay. You agree? Yes. No. That's exactly what I warned you against. What is wrong? Sarah, you've got it.
You've got to look at the block like that.
How do you have to look at the block like that?
Our surface is the top surface, or the bottom surface that we're looking at.
Okay.
The sides.
Okay, so do you say I should move the coordinate system, or what do you think I should do?
So should we not use the semi-rectangular parabola?
Okay, he is suggesting that we should use the other one, like that, something like that. Okay, let me explain to you why I've given you this problem, because it's very, very important. Remember, so many times, I mean, it was so boring. Every time we've looked at something, I told you, remember, everything has been derived for the same boundary conditions on the outside. Okay. Okay. And now you don't have that, because it has been said that you can neglect the heat transfer from the base. Do you agree? So the boundary conditions are not valid. Maar 'n boer maak 'n plan. Okay, a farmer makes a plan, something like that. Okay. Or a mechanical engineering student make a plan. What is the plan? What's the plan? Is somebody there at the back?
Assume the table to have the same characteristics as the air.
Not really. There's a much better plan, yes.
You move your coordinate system to start at the table and you make that as if it's insulated.
Okay, why?
Because it says,
Yeah, I know it says. Yeah, I know it says there's no heat transfer at the bottom, but why? You're right, but the reason is not right. Okay. The reason is let's just look at. Coming back to the short cylinder. With a short cylinder, we've solved that temperature there on the inside as blah, 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 what, 62.3 degrees Celsius. Do you agree? Okay. And that temperature there was 61.7, and that one was 43.7. Okay. So, what will this temperature be here? 43.7, and the temperature there, 43.7 and 43.7. So, where am I going to? Symmetry. Okay. So, anywhere here, if that temperature there is 62, then that temperature there would be 62, that would be 62, and that would be 62. Okay? And then the same, if I look at the temperature there and the temperature there, they would be the same. Okay? So there will be no driving force over that boundary because of symmetry. You agree? Okay. So, die boer maak 'n plan, boer maak 'n plan is, we take that thing, that ice block, and we say, well, let's double the length. Okay, so where previously it was 60, it is now 120. And now I put my coordinate system where they want it. Okay? So I need to select the right dimension here. Previously, you would have made a mistake with that dimension. Now 2L is 120, where previously you would have used L is 60. Simple? Okay. So symmetry can really help us a lot, and many of those problems you need to manipulate to get to the practical problems that we sometimes want to solve. All the curveballs I'm going to give you in the test and the exam. Okay? Any questions? Thank you very much.